As we have discussed before that the change of the magnetic flux through a closed while loop can produce the electromotive force which can produce the current in that loop and also will induce the magnetic field. The change of the magnetic flux can happen in two ways. That is, the change that come from the change of the magnetic field, or come from the change of the area or the shape of the while loop that magnetic field pass through. Okay. Here we will discuss the second case, that is the electromotive force occur from the change of the area that the magnetic field passing through, and we call this problem as a motional EMF. This is we have many applications that can use the results from this discussion, especially we can in the generation of the electric current by moving while loop in the magnetic field. We will discuss that in more detail later, but in this case we will discuss a simple case that if we have a while loop that change the shape and results in changing the area of the loop, and from that the magnetic flux will change and will induce the electromotive force and also the the current and the induced magnetic field. Let's consider the case that we have the while loop like this. This is a while loop, and this T part or edge of the loop is fixed. Okay, and the overall resistance of the loop is R. We may think that we have an ideal conductor for this T part of the loop. So the resistance of this T part are very small, and we connect this with a resistor R. Okay. Now, if this side or this part of the loop can move, okay, and if we apply the force on this loop on this side of the loop and pull it to the right, like in this figure, and let this part move with a constant velocity v, we will see that we need the external force to maintain the constant velocity of this side. Okay, let's say that this side moves with the constant velocity v, which here you can see that the area of this loop is equal to the product of L, which is the width of the loop, and X, which is the length of the loop. So we have A, the area A is equal to XL. You can see that L is fixed, so what is changed in time is X, right? And we have the magnetic field point into the plane of this paper, or the plane of this screen. Okay, and since the magnetic field point perpendicular to the area or the surface of this loop, not surface, the area of this loop, so we can say that the magnetic flux is equal to BXL. In fact, we have discussed this before, that the magnetic flux is the integral of B dot dA. But in this case, we know that B is perpendicular to dA, and B is constant because we have the uniform magnetic field here. So we can say that B dot dA is the magnitude of B times dA. B is constant because we have the uniform magnetic field. So this is the integral of B dA, and dA is the area of the loop, so it's equal to X times L. Okay, so we have the magnetic flux like this. The change of the magnetic flux is equal to the change of this term, which is the d by dt. I will omit the sub B here because we know that the flux here is the magnetic flux. Okay, so we have the dφ by dt is d by dt of bxl, right? But we know that b and l are constant. It's not changed in time, so we can take this out of the derivative. So we have that dφ by dt is bl dx by dt, and dx by dt is the velocity v, right? So we have that this dφ by dt is equal to blv. And from the Faraday law, we know that this dφ by dt is equal to the minus of the electromotive force. But here we want to know only the magnitude. So we can say that the magnitude of the electromotive force is equal to blv. Okay. And once we have the electromotive force, it means that we will have the current passing through this loop, right? And if the overall resistance of the loop is R, so we must have that I is equal to E over R, which is equal to BLV over R. The situation can be described like when this side of the loop moves, we connect a battery or the source into the circuit, okay, and the value or the voltage difference of the source is equal to the EMF, is the magnitude of the EMF, which is equal to BLV. So if we look at this circuit, it means that the current can be calculated as a magnitude of E or a magnitude of E over R, which is equal to BLV. Now, we can see now that when we have the current in the area with the magnetic field, we will have the magnetic force, right? In this case, you can see that when we move this side of the loop to the right, okay, we increase the magnetic flux. So it means that from the Lenz's law, this will induce the magnetic field that against the change of the magnetic flux. Now, if we want to induce the magnetic field that point outward from the plane like this, you can use your the right hand rule. Like if you curl your finger inside the loop and let the direction of the induced magnetic field point in the direction of your finger, your thumb, the current will point in the direction of your thumb. So we must have that the current, the direction of current is counterclockwise like this. And if we look at this side, we have the current, right? We have the current, and when we have the current inside the magnetic field, now this is the magnetic field of the external magnetic field only. Okay, the magnetic field that created by this current will not exert the force on itself, but we have the current in the external magnetic field. Okay, so it means that the external magnetic field will exert the force on the Y that have the current pass through. Again, we can use the right hand rule. Okay, we know that FB is equal to I L cross B. If we look at this side, the vector L point in this direction, right? And B point into the plane. So from the right hand rule, if if L point in the direction of your forefinger, B external, B point out of your palm. So the magnetic force will point in the direction of your thumb. So you have the magnetic force in this direction, right? This is the reason that why we have to apply the force F apply here to maintain the constant velocity V. If there is no magnetic force here, it means that if you apply if you apply a force on this side will move with an acceleration. But in this case, you can see that you need this force to cancel with the magnetic force to maintain the constant velocity V. Okay, so we must apply this force, and the magnitude of this applied force must equal to the magnitude of magnetic force. And since L is perpendicular to B, in this case, we have L cross B, the magnitude of L cross B is equal to LB. So we have the magnetic force which is equal to ILB. Okay, because the magnitude of L here is equal to the small l, right? So we have FB is ILB. And we know that I is equal to this term. So we have the FB is equal to B square L square V over R. Okay. So this is the consequence of the motional Emf. That is when the loop change its size, or the boundary of the loop change, we can induce the EMF in the loop. Okay, and it is interesting to see further that these phenomena follow the conservation of energy. Okay. Since we apply the force on this side of the loop, so it means that we deliver the power into the system, and the power is equal to the force times the velocity. So we have this is a mechanical power that we give to the system. And we also know that there is a current passing through the Y, right? And when the current passing through the Y, which has the resistance, we know that the power that delivered to the system, it means that the power delivered to the circuit is equal to the electrical power, which is equal to IE, because E is act as a source, right? So we have the P is normally we have E is P is IV, but here V is equal to the magnitude of E, so we have P is IE, and we know E is equal to BLV, and I is equal to BLV over R. So this product is become BLV square over R, right? You can see that this BLV square over R is equal to the FB times V, right? We have V here, and if we multiply V, we will have this be V square, which is like this term. So it means that the mechanical power that delivered to the system is equal to the electrical power that delivered to the resistance of the circuit, and we have the conservation of energy in this system.